Good evening and welcome to tonight's webinar from Escape Studios on advanced use of Houdini. My name is Mark Spevick and I'm going to take you through this last part of the series of webinars from Escape, again on advanced uses of Houdini, which is a bit of a strange question because generally Houdini has lots of advanced uses, but we're mostly going to look at VEX and VOPs as a brief introduction. So I'm going to go through that for about half an hour, just so people get familiar with it, because I think it's one context that people are a little scared of. Once you sort of understand the principle of it, it's quite straightforward. And the advantage is it appears in the other context. I'll explain what I mean once we have a look at an example. And then maybe we'll have 10, 15 minutes for some questions and answers, and maybe people can ask for things that they might want to see or learn a bit more about. We'll see if we can address some of those issues very quickly. Let me start first of all, talking about VOPs and VEX. VEX is Houdini's sort of internal language, and it's a coding language that you can write code for. Obviously, with Houdini, we do a lot of stuff with nodes, and there's a node-based context called VOPs that allows you to write VEX code. You can also write VEX code directly in text files, or you can write snippets of VEX code to do some very cool stuff in Rangle nodes. So Rangle nodes and VOP nodes are very similar in the kind of things that you can do with them. They bring a whole new level of customization that you can do with Houdini. Let's have a look and see what we can do with that. I'm just going to drop down a grid for now, and just let's just frame that. And because we're going to be dealing with the points, I'm going to increase the resolution of the grid quite a bit, so you have a nice number of points there to see what's going on. So normally with Houdini, it's all about the points, which you can see down here in the geometry spreadsheet. Each point has an attribute called position, P, which has its world space position. That's a position in world space, actually. That's the minimum attribute it kind of needs. And we can add other attributes, say normal or UVs, etc., to manipulate and the geometry or do things that we like. So if we actually change these numbers, for example, if I move the center here up to 1 in Y, you'll see that the position in Y has gone to 1 because we've added 1 to the position in Y and it's risen up. So we can do this kind of thing in a node. Now, what's nice about VEX and VOPs and things like that, it allows you to manipulate the geometry point by point. So we can kind of do these things in VEX and VOPs. I'm going to start with VOP nodes first off, and then we'll move into sort of VEX coding, and then we'll talk about the differences between them. So to go into VOPs, you hit tab and type VOP, and you'll see there's quite a few types of VOP that we can choose from. Now in Houdini, as you know, we deal with different types of geometry, for example, volumes or maybe height fields, or just general polygon geometry. And within polygon geometry, we deal with the different attribute types. For example, we can deal with points or primitives or vertex. So depending on what you're dealing with, you choose the relevant VOP. We're going to be dealing with points. I want to move points around and manipulate them rather than primitives or vertices. So I'm going to click on point VOP and we'll drop one in. I'm going to plug this into the first input, turn it on, and we'll dive inside. Now before we do, actually, we'll look at the interface at the top here and we'll see it's actually being compiled. And it's because it's actually generating VEX code. We'll look at that in a moment. I'm just going to dive inside and you'll see a couple of nodes that look a little different to the nodes that we're more familiar with up in SOPs. Now, most of the different VOPs contexts, I mean, what I mean by that is in, for example, all the contexts. So if we go to shops and we hit VOP, we'll have a VOP network. And if we go to chops, let's just make a chop network and dive inside. Hit VOPs, we'll get a VOP network again here. If we go to compositing, dive inside there and hit tab, we get a couple of types of VOP as well. And if we go into output, we get another VOP network here. So we can put VOP networks in most contexts that allow us to manipulate the data in those contexts. In SOPs, we're manipulating point and geometry data or volume data. But for example, in compositing or manipulating pixel data. But the principle remains the same. In all VOPs, you'll have an input node and an output node. The input node allows you access to some variables that already exist in Houdini. A lot of these variables may or may not be there depending on what you're doing. For example, we haven't got velocity or age, so these will return 0, but we do have P. Now this doesn't change depending on what you plug it into. These variables are always there, but if there's no data, you'll just return the default value, which often is 0, but it could be other numbers. So we have a value at P, which is the current point position. Now, you're probably wondering how these, well, this manipulates all the points, but how does it iterate over all the points? It doesn't loop. It doesn't do the points one at a time or sequentially. It actually does them all in parallel, all at the same time. So whatever code that we plug in here, Houdini just applies to all the points all at once, without regard for any other point near or next to it. So it's not actually a loop as such, but it works in parallel, which is very, very good and very fast. Yep, that's why we can enable multi-threading on here, because it works in parallel. So what can we do? Well, first of all, we can plug position. Oh yeah, that's what I'm saying. These are the input variables. These are the output variables. And these are the things that we can change, things like position, velocity, but we can output any other variable that we like. I'll show you how we can do that in a moment. So we can put our own custom data in and out of the system. So very quickly, let's have a look at what we can do. If I plug, we can take the noodle out, or the connection, and plug one into the other. So I'm plugging position into position, so effectively I'm doing nothing. And if you remember before, we added some data to the P to change it. So what I want to do is add something to PY in order to move this up the y-axis. So that's very simple. This is visual programming, and we can do that kind of maths. So I said I wanted to add something to position. So if I hit tab, I can type add, bring in an add node. If I drop that in, and to the to position, I can add something else here with this other input. Now I'm going to add a constant number. So I'm going to hit tab and type constant. And I want this to be a vector, because position is a vector. So we'll change float to vector. A vector is just a bunch of 3 numbers. So there's my x, y, and z, if you like. So I'm going to add that in. So at the moment, I'm adding 0, 0, 0 to P, but I want to add something to PY. So I would change the middle number here. As I change that, you'll see that our grid moves up. And you'll see P does in fact change. So 0.5 here, and that was 0 to 0.5. I can also add something to the x and to the z as well if I want. So this is basically a transform. I'm moving it around by adding numbers to P to move my thing around. Now we can add something a bit more interesting than P. Sorry, a constant number here. Actually, there's another feature of the VOPs that I can show you. We can build an interface with this. If I delete this, I still want to add a constant number, but if you middle click on the input here, you can bring up a menu. Now, if you choose promote, see you've got a constant there, so we could have chosen it from here, but we can also choose promote parameter. If I do that, we get a funny little noggin. If you click that noggin, you'll see it's actually it's actually a node called a parameter, and these are the inputs for it. Now I'm going to call this offset, because that's effectively what it's doing, and I'll give it a label as offset geometry. Now the reason you give it 2 names is this is the name you're going to use in expressions, and this is the label that the human reads. So you want this to sort of be easy to understand. Now you can actually double click on this noggin and it will show you that it is a big node. Just easy to select that way. Now what has this done? Well, if we go up a level, you'll see at the bottom of this interface we now have a little slider here, and it says offset geometry. If I hold my cursor over it, you'll see the parameter is offset, which is what I typed as the bit for the code. But you'll notice it's just a float at the minute. If I go inside, we'll see our parameter is set to float here. I need this to be a vector. Now if I go up one, we'll see we have our vector up here. And again, I can control it from this level. Just saves me having to keep diving inside this network and edit and finding nodes to edit. Now we can do something a little bit more interesting to this. In maths, we have a sine function. A sine function is a wave. You put in a number that changes, and it returns a number that cycles between -1 and +1. So if we were to hit tab and type sine, you'll see we plug in a number that changes here, and this will return out the other side a number that varies between -1 and +1. So let's put in a number that changes for that, and then we will add it into our equation here. Now I'm just going to delete this add and this offset for a minute. If I go up here, you'll see that parameter has disappeared from the interface. And I want this to change. Now I want the number to change across the x-axis. So imagine px changes as we go along the x, pz won't. Likewise, if we move along the z-axis, px won't change. But if we look here, these are vectors, which means they're made up of 3 numbers. Now there's different data types, and when it comes to coding, there's vectors and ints and floats. If you hold your cursor over there, it'll actually tell you at the bottom it's p, and it's a vector. This one is v, and that's a vector too. You'll see these light green ones, they're in floats. So that's a floating point number. And then we've got these blue ones, which are integers. Okay, so these are other integers down here. And these pink ones, they're strings. Then they're path to, well, op input 1 is actually, if we go up 1, this input. Op input 2 is the second. Op input 3 is the third. And op input 4 is the fourth. So here we can load in other geometry and read attributes from that. And mix it in with the current geometry, which is kind of interesting. So I want to access a part of this. Actually, just a quick aside. You're probably wondering, when you're new to Houdini, what do these variables mean at the moment? Because P or V, they might be a bit random. There is a way to see this. If I pop up into the interface, and I go to window, where are we? One of the preferences window, so edit, preferences. Which one is it? Let's go to this one here, network, editors, nodes, and trees. You'll see here we have display, VOP, input, and output descriptive labels. If you turn that on and hit apply, you'll see now that we have a better explanation of what these attributes are. So it tells you velocity, force, CD you'll still have to know, UV, etc., etc. But this is a bit, I don't like this too much actually. If I turn that off, hit apply, these are actually what you'd use in coding. I'm going to show you a Rangle node shortly, and it's these names here that you'd use in a Rangle node. So yeah, let's quickly check this out. So I want to access a single part of this vector here, the position. So if I hit tab and type vector, I can see I can get a vector to float node. If I plug that in, this will just give me an error for the minute. All the points are there. You'll see they're just zigzagged along. We won't worry about that for a moment. But what I've done is I've plugged the vector in, and this has given me access to the X, the Y, and the Z components of that. So I'm basically plugged all the X coordinates into the overall position, which is why it's given me that funny geometry. Now, we can actually do the reverse of this. Instead of converting a vector to a float, we can hit tab and type float to vector. And here we can put our, let's put that back in. We can put our 3 floats, our X, Y, Z, back into a vector, which we can plug back into position. So if I was to plug all this across, it's effectively doing nothing again. Now the advantage of that is I can access each one of these components individually. Now what I want to do is plug the X component into sine, so it's going to vary across the X-axis. And what I'd like to do is plug that sine into the Y instead. So ignoring the original Y position, which was 0, and now as X changes, we're seeing that sine wave come in, and we've created a sine deformer along the X-axis. If I was to plug in the Z-axis, it goes along the Z-axis, because that's the number that changes, not X. Now, we can increase the frequency of this. If you want the number to change more often, what we can do is we can multiply the input number here, so it changes more quickly. So if I hit tab and type multiply, I can multiply this up. So I'm just going to create another parameter here, which I'm going to call frequency. And if we go up 1, where are we? I increase the frequency. You'll see as I speed up that number, we get more waves. Now the height of the waves is the amplitude. that's how much I'm putting out here. At the moment, I'm bringing out -1 and +1. If I was to multiply that up and down, I can choose the scale of that and have it go between, say, 0.5 and +0.5 or another number. So I want another multiplier on the other side here for the height, and we call that amplitude. So let me just pop another multiplier in here. Middle click and create a promote parameter. And we'll call this amplitude. So now if I go up one and I increase the amplitude, we can control the height. Now, there's another interesting thing that we can do. We can take a number that changes, instead of a number that changes across here, we can change a number that, use a number that changes radially. Now, there's a nice trick where we can work out the distance from a 0 point here. What I mean by that is if we look top down and we look at the origin, if I draw a circle around the origin, every point on that circle is at the same distance. Okay, and if I was to take that and move that further away, you'll know that the distance increases along that circle. But at each circle, they've all got the same number as it radiates. So what I'm going to do is I'm going to create a number that changes from the center out in radiating patterns, and that should change my sine wave into radiating patterns. Now to do that, we can measure the distance from a point, from the current point to the origin, for example. So if I measure the distance from here to here, this point will give me a value, and this point will give me the same value, etc., etc. So let's have a look at what I mean by that. So if I hit tab and type distance, this will give me the distance between 2 points. So 0, 0, 0 will be the origin, and we'll measure the current position here, P. Now, if I use this instead of the X and the multiply, we'll see that the number that I've chosen, instead of changing as you go across an axis, it actually changes as you radiate out from the 0 point here. If I offset the 0 point, it radiates from the point that I'm taking away the current position from. So if I move that to -0.8, you'll see it radiates from -0.8. Oh, there we go, -0.8. So we changed our sine deformer into sort of a wave deformer. Now I'm actually going to promote the parameter of this position here. So we'll give that a, undo that. We'll make this a promote parameter. Again, we'll call this a vector. We'll call this location. Oh, it's actually origin, isn't it? Let's call it origin. If we go up one, we'll see our little parameter here. We can change the origin. Now, if I move the time, you'll see time doesn't change. The way to get time to change it is to actually offset this number here with a frame increment, or with an increment. I'll show you what I mean. Let's add an offset. So let's put an add in. Again, we'll promote a parameter. We'll call this time. So with time at 0, nothing's going to happen. But the point is, if I change this value, you'll see it's offsetting our number that we're feeding into the sine function. So instead of 0, it's 0 plus 2, and every other value plus 2, so it's offset it all. So we can actually link this to time using another expression, say $FF, which links to the floating frame. And if I press play, we get our sine wave radiating inwards. Now, if I want this to go in the other direction, we simply just put a minus here, and this will give us the opposite direction. And we can also put a scalar in here, ×2. But again, this is awkward. So we could actually link that in down here. Now, instead of promoting this parameter, let's delete that. And we know that we wanted to plug in time. So look, here we have time, but actually there's the frame that I was using. So I'm going to plug in frame. Now, some would say, what's better to plug in, time or frame? Well, actually, it's better to plug in time. The reason it's better to use time instead of frame is if you're using frame and you play things back at a different frame rate, your timings of your animation will change. If you use time, on the other hand, that's seconds. That's in seconds. So even if the frame rate changes, the timing is always the same. It will always happen at 1 second. So time is a little bit more stable if you don't know what frame rate you're going to end up using. But most of the time, in at least movie production, you always work on 24 frames a second, so it doesn't really matter. But you should be aware of that fact, because if you are changing the changing the frame rate of your animations, then things will be wrong if you're using frame instead of time. It'll all change. So we want to again multiply this so we can make it faster and slower. So if I promote this parameter, we'll call this speed. Because this will multiply up the time increment, it can make it go faster or slower. So speed of 0, we're adding 0 increments. So 1, we're adding a rate of 1, or 2, or 3, 0.1, or -2. Now that's a bit annoying, keep doing it. I'd rather have that as the default, so that's easily enough. We can also multiply this number by a constant, and we'll call this constant -1. So it's always going to inverse that number. So if I put 2 in now, it will go in the right direction. Because whatever number I put in, I'm multiplying by -1. So we've made a sine wave deformer using this VOPs, where we can run through the frequency, and increase the amplitude or decrease it. We can move the center of the deform, and we can change the speed. We built a little interface for it. So VOPs are very powerful. You can sort of do custom things like that, although there is a bend deformer which does a very similar thing, but we built our own. Now, let's have a look at the sort of the Rangle nodes. So I'm going to hit tab and type Rangle, and we'll see that we have again different geometry types there. Again, our volume, primitive, vertex, point, etc. Again, I'm dealing with points. I'm going to choose the point Rangle. I'm going to plug it in. Now the point Rangle is just where we're typing code. Now if I look at the point VOP actually, and I right click on it, I can choose VEX and VOP options, and I can actually view the VEX code this has generated. So that node has generated this code. Looks pretty scary. Don't be scared by that. It has to generate this kind of funky code because of the way the nodes work and have to work together. We're going to write a similar code, but no way we're going to write anything as convoluted or as complicated looking as that. So here we would write our code to do a similar thing. So again, we have to type in things to access these variables or these attributes here. Now there's an easy way to access these attributes in Houdini. We use the @ syntax. So @p would pull that data. Now, in order to test that, I can also create attributes here. So to create an attribute there, let's create a vector. Let's call it vector @bob. You need the semicolon so we know it's the end of the line. And you'll see we've created a vector attribute called bob. So you say v vector @bob, and it creates your attribute here @bob. If I was to call this f for float, I would get a float for bob, or indeed an I, so integer. I'd get a whole number, integer. Let's have it as a vector. And I could say it was equal to @p. And you'll see it's taken the value of p and it's read it into this attribute and created it called bob. The reason it creates this attribute called bob, because down here it says attribute to create with a star. So any attributes we call with this syntax and it doesn't exist, Houdini will make it and populate it with the numbers we want. So look, I could tell it to fill it with this numbers here, 1, 2, 3. We get our 1, 2, 3. So you can fill up your own data with these variables. So let's do something similar to what we were doing with the point VOP. So I want to manipulate the position. Now, if you think about it, the position is a vector and it's got these 3 components. We can access these through the indices. If we look at these 2 vectors here, for example, you'll see this is referenced with X, Y, and Z, and whereas Bob is referenced with 0, 1, and 2. And actually, if I look at CD, oh, see, I didn't put the at in. Now it knows to make it. Oh, let's give it a value. We'll give it red. There we go. You'll see CD is referred to as R, G, and B. So which one is correct for these vectors? Well, actually, we can access all of them in the same way. When we refer to a vector, we could say at P dot X for the X position, or R, or 0. All of those will allow us to access the X or the first index of that vector. I'm going to keep it as X because it makes sense for the position. Actually, Y in this case, because we want to manipulate the Y. And I'm going to say it equals sine, and this, as we did before, at P dot X. So as P dot X changes, sine will change between -1 and +1 and change the Y. Now, actually, I can get rid of these bits of code by hashing them out like this, or // them out. We can type comments like this so we know what our code is doing. But there you go, we've got our plugging in the changing position in X into a sine, gives us a number between -1 and +1. The position Y changes as that position in X changes. Again, if I was to change this to, instead of X, I was to use R, that's in the red, or the first option, or 0, that's all going to give me the same thing. Oh, maybe not P dot 0 then. So we can use R or X. So if I was to change that to Z, it's using the other axis. It's very similar to what we did before. And again, if I multiply this, that's going to change it more often, and that's our frequency. Now, it's a bit awkward, again, to keep typing this in here. And like with the point VOP, it'd be nice to make an interface for it where I have a slider. And that's very easily done with a Rangle. In VEX, we can use a ch expression. In fact, we've seen the ch expression in HScript in normal nodes, but you can also write it in VEX, and it works the same way. You give ch, and you give it a path. Now I'm going to just give it a name of a parameter or variable that doesn't exist. So I'm going to call this frequency, or freak. And I want this variable actually to be a float. So I'm going to do CHF here, CHF. So this is going to make a channel of a float called frequency. I'm going to multiply it by px. Now if I hit click out of there, it gives me an error because this returns a 0. There is no parameter called frequency on this node. Now we could make one with the parameter interface, but in VEX it expects you to have lots of these sliders. So we have this magic little button at the side here. When we click on here, this will scan the code, and if there's any channel expressions to a channel that doesn't exist, it will create it on the node for us. So if I click on here, it'll automatically create my floating channel here, slider for frequency. If I increase the number, you'll see that increases our frequency for us. So just by writing that channel expression, it's very easy to make an interface below here. So remember how we increased the amplitude? We multiplied this whole function by another channel called amplitude. So let's just call that amp like this. And again, this wants to be a float. Doesn't exist yet until I click the magic button. There's my amplitude. I have a slider and I've got the frequency. We can do our time thing again. Now I can't remember what the variable was for time. I can do at to access it. Now if I dive inside the point VOP, we can see it's actually called time here with a capital T. So in my Rangle, to use time here, remember we wanted to take this number and we wanted to add time to it. So let me open up the sign here. We'll add time. Now I have to put the at in front of it so it knows it's pulling in that data. And look, now we have a little time stamp on their little clock. If I press play, you'll see that changes. And we wanted to multiply time by speed, like we did in the VOP. So I'll put brackets around here. We'll go times. We'll call this channel. Well, again, this is a float. Speed. Click our magic button. Oh, I need to put another bracket in. There we go. So there's our speed number. So if I press play, 0 does nothing. If I put 1 in, it starts to move. We'll start to see the offset. That's working quite nicely. Cool. And we can extend that a little further. So like we did before, we worked out the distance between 2 points. Okay, so let's create a variable for that. So I'm going to call that f at distance. Can't spell that. D-I-S-T-A-N-C-E equals, and you'll see there's a it's not a good idea to create variables with the same name as a command. You'll see the command pops up as I time it. So I'm going to call this dist actually equals distance. The reason why it's not a good idea, Houdini doesn't know if you're calling a command or a variable. So I'm going to call f at dist equals distance, and we give it 2 point positions. So I'm going to give it, the first point position was going to be a slider, if you remember. So that would have been chur v for a vector. We'll call this origin. And then a comma, and then we give it the other position, which is at P. And we'll see our distance there of our guys. And it's this effort distance, which I'm going to copy. And instead of the P.x changing here, that'll be our effort distance. Now we get our radiating circle. And again, if we increase the frequency, or the amplitude, or the speed, and we can move between those. So we're doing the very, very same thing with both networks here. Oh, hang on a sec, I've got to click my magic button, and now I get an origin. Forgot to do that bit. There we go, we can offset the origin. Move it that way. So we see we've got two nodes doing exactly the same job. One was put together using sort of these nodes in a visual sort of codery way. But we're doing exactly the same maths as we wrote in the code here. To some people, this may seem a lot more simpler. To other people, this might be a lot more intuitive and simpler, but essentially we're doing the same thing. If I again look at the code generated by these nodes, you'll see it's we're calling in our position ones here. Oh, I want to edit that. And the rest of it. Where are we? So look, there's the distance expression that we used. There we're bringing in our origin and our other guy. And it's taking the result of that, and we're multiplying the time by the speed. And we're multiplying the distance by the result of the time and the speed. So we're adding the distance there. And then we're taking the result of this, and we're multiplying that by frequency. As you can see here, it's just broken it down into separate lines because each node was doing that individual bit, and it's put each of those lines of code in sequentially. Whereas here, we wrote them all in one line, maybe a lot harder to read. But essentially, we're doing exactly the same thing to that data. It all depends which one seems more intuitive to you. So hopefully that's given people a slight bit of understanding on how VOPs and Rangle nodes work. They're doing the same job. They're just allowing us to manipulate the individual attributes on the points as we go. And we can do some very funky stuff if we know a little bit of maths and a little bit of creativity. And you can build all sorts of interesting deformers and manipulators and other bits to do some very, very cool things. Okay, so the difference between, if we can do the same thing in both of these, what would you want to do differently in them? Well, it's a matter of taste, really. I think it's often easier sometimes to do quick stuff, writing a few lines of code. But if you're doing much more complicated things, sometimes it's a little easier to use the point VOPs. For example, if you're using a lot of noise expressions, they're quite a bugger to type. So it's a lot easier to use the VOP nodes because you can just plug in those noise expressions. But again, it's really up to you and your matter of style. I think it's easier to create geometry in the Rangle nodes than it is the VOP nodes, but both will do just a fine job. Let's add some noise with a new one. So here I'm just going to add another VOP, and we'll do this with some noise. With a point VOP, I mean, we'll add some noise or some patterns. So I'm going to hit Tab, and if you look, there's a pattern section. We've got lots of nice little patterns here. So let's have a look at the rounded stars, for example. Oh, you'll notice the rounded stars actually looks for UVs instead of P for position. Let me hit Tab again and type anti-alias noise. This uses P position for a lookup. So this is, remember, in the geometry, in texturing, we have 3D and 2D textures. 3D textures, we look up a world space position to find out the colors. That's this P. So position is world space. Whereas UVs uses the UV coordinates in the geometry and looks up a 2D space image. So that's what this requires. We don't have UVs on this guy yet, so let me make some UVs on him. So I'm going to hit Tab and type UV texture. Let's just make sure this is a point attribute and it's projected down the Y. So if in space 5, I can see my UVs. Now in the point VOP, we now have UVs. Now they were always there. See, there's a UV plug. But it was 0 before we actually created some meaningful data, because look, here now is a UV attribute. So first of all, let me plug my UV in so we can look up the texture correctly. And I'm going to plug now the amount, if you look, is a scalar and color is a vector. So this is going to return one value. Now, if I plug that into color, you'll see we get a dotted line, even though it shows me something. The dotted line means I'm doing something a bit dodgy. I'm converting the data type. I'm changing from a float to a vector, but I'm not controlling how it's doing the numbers. In this case, it doesn't matter. I'm getting the same value in all three parts of the vector, so we get a black and white image. But it makes sense to do this properly. So again, if we just use a float to vector, we can just plug it in. So there you go. We'll just plug it in just the red channel, and that means the green and blue are 0, so that's why it's red. Obviously, if I put that in the green, we've got red and green mixed, and then red, green, and blue mixed give us our white. Now, there's various parameters here that we can change. For example, the frequency, or the offset, or the randomness. We can change the star size relative to the rest, or give them random sizes. Let's make loads of those. Can make them more round. Oh, see, we haven't got enough squares to resolve them. Let me just revert this to defaults. So we can change the roundness of our star and the softness and the blur, which won't just seem to do very much. Now we can do some interesting things with this. We can also add some noise here. So this will use P for a world space position, a 3D position. And again, this is an interesting one because you'll see here the signature. This is the input, this is the output. We plugged in a 3D input. It means it's got 3 dimensions, X, Y, and Z, the position. And this is returning a 1 dimension, in other words, a float. So if we plug this into those 3 slots, we'll see the result of that noise, a black and white noise here. Now, I don't have to return this. I can actually return a 3D noise. You see we get the error there. Let me plug that into color directly, and you'll see that's a 3D noise. It's giving us a different noise in all the X, Ys, and Zs, or the RGs and Bs, which is why we see color. So you can either have a color noise or a scalar noise if you want, depending on whether you choose that up here. So again, we have frequency and amplitude. Can bring down the numbers of layers of noise in there, etc., etc. Now I'm going to set this back to 1D noise, and we could do something very interesting with this. Now again, what I'm going to do is, very briefly, I'm going to add a sphere. Let's make this a polygon sphere with lots of frequency. Let's plug that in. More frequency. There we go. You see the noise mapped to the sphere. I'm just going to add a normal here, which will add some normals to our sphere. As you can see, they radiate outwards. Now, with my noise here, I'm going to make a vector to float again. And I'm going to do an add. And I'll add to the Y position my noise. And then we'll do a float to vector. So plug our Y back in, our X, and our Z. We'll put the result into position. That's kind of a bit crazy. Let's just revert this to the defaults. So that's a 1D noise. So yeah, we're adding that to the Y positions, and we get this funky thing. Because we don't really want to add it to the Y positions, that would probably work for a grid, or maybe not. Why is that not working for a grid? Let's just plug Y back in. Oops, something's gone a bit wrong. Oh, look, I plugged velocity and not position. That's why it was going a bit nuts. Right, let's plug the Y. There we go. If we plug the Y position in, you'll see how we're adding. Let me turn off the color because it's hiding things. There you go. So you can see how we're adding the Y to the grid. But if we do that to a sphere, it doesn't look very good. All right, it's just adding to the Y position. We don't want to do that. We want it to add it to the normals, actually, so it radiates out in all the directions. We get away on the sphere, on a plane adding to Y, but not geometry with a non-planar shape. So we don't just add it to the Y here. Let me get rid of these guys. What we can do actually is use a displace along normal node. And this will actually move the point P, which we can plug in there. So P to P. And this will move it along its normal. So we need to plug in the normal to know which direction to move it along. Where's N? There it is. Now that we've made N with the normal node. And the amount is how much push it along that normal. And this is our new position. You'll see it now radiates out correctly, a bit like the mountain sop. In fact, this is a mountain sop. I need to recalculate those normals so we can see the shading correctly. And in here now, I can play the noise on my 3D shape. And like I said before, that pretty much is what the mountain sop does. If I just plug the mountain sop into the sphere, you'll see again, it's you'll recognize the noise settings here. Very similar. We dive inside the attribute VOP. There we go. Look, unified noise it's using. So you can see how that one's wired in pretty much similar to what we've built ourselves there. So these are very, very versatile things for manipulating point numbers, values, attributes, etc., which makes it all very, very interesting. So hopefully you've enjoyed today's webinar, a little introduction to the more advanced side of Houdini, and that's sort of dealing with the points and their data directly using either Rangle nodes or VOP nodes, whichever you would find more intuitive. It really doesn't matter as long as you do the right job in the most efficient way. It's whichever you feel more comfortable with. But hopefully I've demystified that a little bit. There's some fantastic resources I want to point you to. There's a great website called Tokaru by Matt Estrella. Houdini CG Wiki here. This is fantastic if you want some very, very good reference on VEX and start to learn it. You go into the Houdini menu up here. Let's hope it loads up. You'll see there's a VEX section. There we go, VEX. And here's a lot of examples on bits of VEX code that you can do. Again, it goes through some very nice tricks and tips. And also you can look at VOPs. So here, there's some very, very nice tips and tricks on using VOPs and some example scenes as well. And it'll just give you an idea of some of the very, very cool things that you can do. As always, the interface itself is fairly easy to understand. Where it really comes into its own is knowing and remembering and learning these techniques that you pick up. So this website is a fantastic resource as a starting point to get yourselves a bit more into VEX and VOPs, which I fully recommend. It's a very, very easy, usable, customizable part of Houdini. So I just want to say thank you guys. Thank you for taking the time to listen to me. And then hopefully, if we do some more of these webinars, we'll inform you and we'll catch up with you guys soon. Keep smiling, keep warm, and take care. Cheers, guys.